So my name is Helen, and I'm a master's student in Dr. Hakidatu's lab. And today I'll be talking about my thesis project on developing a universal antifouling and antibacterial coating for platelet storage devices to extend shelf life and improve transfusion safety. So here is an overview of my presentation today. First, I will go over some background information on platelets and the problems facing current platelet storage devices and practices. Then I will talk about the approaches that are used currently to address these problems, their advantages and drawbacks. This will then bring me to the rationale for my project and the goals and objectives of my work. I will then present some preliminary data and end with future work. So, as you all probably know, platelets are cells in our blood that stops bleeding. And for patients with a low platelet count or poor platelet function, they require transfusions to prevent and treat bleeding. So, for example, people who are actively bleeding, preparing for surgeries, or cancer patients undergoing chemotherapy. However, platelet units have a short shelf life, which leads to a lot of waste and shortages. So currently, platelets are stored in plasticized polyvinyl chloride containers at 22 degrees Celsius for a maximum of 5 to 7 days. And this short shelf life is attributed to two main causes. First, platelets undergo deleterious changes in structure and function over the storage period due to various mechanisms, and one of which is unfavorable interactions with the surface of the storage container, and this leads to decreased circulation time and hemostatic activity after transfusion. Storage at room temperature also makes platelets susceptible to bacterial contamination, as the storage conditions are ideal for the growth of many bacterial species. And this can be devastating to platelet transfusion recipients, as many may be immunocompromised. So currently there are two major ways to address this problem. Preventative measures such as donor selection, disinfecting the skin prior to withdrawal of blood, removing the first aliquots, and regular testing. These are very easy to implement and are generally effective at minimizing bacterial contamination. However, even the most advanced tests have detection limits, and with these measures in place, approximately 1 in 2,500 contaminated units still escape detection, leading to adverse and sometimes fatal transfusion reactions. Pathogen inactivation technologies represent a newer, more proactive approach by using ultraviolet light to target the nucleic acids of pathogens. This approach addresses the gaps in the preventative measures and further increases transfusion safety, but UV light is non-specific and may cause damage to cells, resulting in decreased circulation time and hemostatic activity after transfusion. A third and emerging approach to address this problem is to modify the platelet back surface, since platelet and bacterial adhesion are strongly dependent on the chemical and physical properties of that surface. So the hydrophobicity of the current PVC bag is not only conducive to bacterial adhesion and biofilm formation, but also the absorption of proteins and subsequent adhesion and activation of platelets. We propose to overcome this by developing a hydrophilic polymer coating, as they have shown many advantages as antifouling coatings. However, their translation from laboratory surfaces to biomedical plastics is difficult because of the wide variety of commercial platelet storage containers that are available, and they often have proprietary compositions and highly variable characteristics depending on plasticizer type and quantity. So the goal of my project is to address this problem of platelet storage through an antifouling coating that is adaptable to a wide range of materials, that is resistant to the adhesion of platelets and bacteria, and are capable of preserving platelet quality during extended storage. So to do this, we will use interaction between polydopamine and known hydrophilic polymers to coat the platelet bags. Then we will incorporate antimicrobial peptides to actively kill any potential bacterial contaminants. So using this method, I have performed some preliminary platelet adhesion tests on different polymers. So first I coated the platelet bags using the hydrophilic polymers and dopamine mixture, and I cut the bag into these coupons and incubated them with plasma-rich platelets. And after washing to remove any unbound platelets, I added detergent to lyse the cells and incubated them with an LDH catalyst and dye, which allowed me to quantify the number of platelets bound to the coupon via absorbance measurements. So here are the results of 5 different polymers at polymer and dopamine ratio of 5:1 and 15:1. So as you can see, PDMA, polyacrylamide, and PMPC at ratios of 15:1 reduced platelet adhesion by over 90%, and they are candidates for further long-term storage tests. So we're also interested in looking at the bacterial adhesion on the coating. Using the same method, we incubated the coated coupons with Staphylococcus aureus, and after washing to remove the unbound bacteria, we quantified the bacteria adhered onto the surface using plate counting. And here are the preliminary results that show that PDMA coatings were effective at reducing bacterial adhesion. In particular, the coating composed of PDMA to dopamine at a ratio of 15:1 performed the best, reducing bacterial adhesion by approximately 83%. So in summary, our preliminary platelet and bacterial adhesion tests show that the polymer and dopamine coatings were effective at reducing bacteria and platelet adhesion. Moving forward, we will expand bacterial adhesion tests to our library of hydrophilic polymers and then introduce antimicrobial peptides to the top performing candidates to actively kill any bacteria. And I would like to thank everyone in the Kiyosaki Datu lab, especially my PI, for their encouragement and support. And that concludes my presentation. I would be happy to take any questions. Thank you.
Thanks very much, Helen. This paper's open for questions.
Hi, it's Ed Prysdale here. Thanks very much for that great talk. I'm wondering about the possible toxicity of remaining soluble forms of your various polymer compounds and the initial products, the initial starting materials. How do you make sure that that's out of the bag?
That is a very good question.
We sure don't want to be putting that into somebody's arm.
Yes, that's true. So to make sure that these polymers are not to make sure that the antibacterial activity of the coating is due to the antimicrobial peptides itself and not the polymers and whatever is in the polymers. We do purify the polymers to remove any potential initiators and catalysts that are toxic. And we also, and yeah.
Thank you very much. Any other questions? Thanks very much for a great talk.
Yeah, thank you, Helen.